So in our last lecture series, we discussed solubility product constants, what they were, how to write them, and also why we are concerned with dissolving salts in solution or possibly precipitating salts out of solution. So here what we're going to focus on is how can I write these ionic equations? Also, how can I write the solubility product expressions for each of these salts? And this is going to be an important step because you're going to use this for every single solubility problem that you see from here on out. So if you don't understand this, go back and rewatch because this is going to be kind of the foundation of how you're going to set up each problem. So we want to write the ionic equation and the solubility product expression for each of these salts. And the salts I've been provided are silver iodide, calcium carbonate, magnesium hydroxide, magnesium ammonium phosphate, and that calcium hydroxyl apatite that we saw earlier that's present in your teeth. So on the next slide, I've worked through this problem. So for our silver iodide, the first thing we want to do is we want to write our ionic equation for it. And so we're going to start with our solid. So we just have our silver iodide solid, and then that's in equilibrium, and it's going to end up forming the silver ion as well as the iodide ion, both aqueous. So when I write my KSP expression, my KSP is equal to the concentration of products divided by reactants. And in all of the cases for these salts, I'm going to ignore my reactants because they're always going to be a solid salt. So here my KSP is equal to the concentration of the silver ion times the concentration of the iodide ion, each raised to a coefficient of 1 based off of the coefficient that was in front of each respective ion. So the next one we have is calcium carbonate. In the case of calcium carbonate, one of the hardest parts for students is they can't recognize what is an ion and what isn't an ion. So some students will try and break it up into its elements. So they'll break it up into calcium, carbon, and oxygen. You do not want to do that. You want to recognize what ions make this salt. So this salt is made up of the calcium ion, so calcium 2+, as well as the polyatomic ion carbonate. So it is important that you guys remember your polyatomic ions from your Chem 151 course. So for this particular salt, calcium carbonate is my solid. I'm always going to start there with my ionic equation. And then it's in equilibrium and breaks down into the calcium 2+ aqueous ion and the carbonate 2-. This should say 2- on there, aqueous ion. So it's just a 1-to-1 breakdown. So 1 calcium for every 1 carbonate. Then when I write my KSP, it is equal to the concentration of the products, calcium 2+ times carbonate 2-. And I'm not going to raise any to a coefficient other than 1 because their coefficients are 1. It's a 1-to-1 charge balanced compound. So that's going to be my KSP expression or my solubility product expression. The next one we have is magnesium hydroxide. That's going to break into its respective ions of magnesium and the hydroxide ion. So for magnesium hydroxide, I'm going to write its solid, so magnesium hydroxide. And then I'm going to break it down into its respective ions for my product. So I have magnesium 2+ aqueous, and I'm going to have 2 hydroxide ions, -1 charge, aqueous. So it's important to note that for every 1 magnesium, I need 2 hydroxides, and that's going to be represented by the coefficient in front of my OH-. When I write my KSP expression, my KSP is equal to the concentration of magnesium times the concentration of the hydroxide ion, and we're going to raise that hydroxide ion to the power of 2 because of its respective coefficient. So make sure you're raising each one to its respective coefficient. The next one, we have a salt of magnesium ammonium phosphate, and this is kind of a weird salt because it actually has 3 ions present in the solution. It has 1 anion, that would be the phosphate, and it has 2 cations, the ammonium and the magnesium. In this class, you guys will never be tasked with finding the ions present in a salt that will break up into 3 respective ions. So on any exam or any homework problem, really what you're going to focus on is you have a salt and it will break up into 2 respective ions, a cation and an anion. So you're not going to see many like this. So we have our solid magnesium ammonium phosphate, and it breaks down into its respective ions, magnesium 2+, ammonium+, and a phosphate 3-. Each one is a 1-to-1-to-1 ratio. So when I write my KSP, it is equal to the concentration of magnesium 2+ times the concentration of ammonium times the concentration of phosphate. The very last one we have is that calcium hydroxyl apatite, and this once again has 3 ions present. The cation is my calcium 2+, and the 2 anions are a phosphate 3- and a hydroxide 1-. So we have our solid calcium hydroxyl apatite. It's in equilibrium, and it breaks into its 3 respective ions, 5 calcium 2+, 3 phosphate 3-, and 1 hydroxide group. So when I write my KSP expression, it is equal to the concentration of calcium 2+ raised to the power 5 due to its respective coefficient, times the concentration of the phosphate raised to the power 3 due to its respective coefficient, times my hydroxide ion, just raised to the power 1 because it's a coefficient of 1. Like I said, D and E are going to be more complicated than what you're going to see in this course, but you should be comfortable with A, B, and C. So it is important that you do know your polyatomic ions, so you're not break them into their respective elements. So KSP and solubility. My solubility is the maximum possible concentration of solute in a solution at a given temperature and pressure, meaning that if I dumped, let's say, 2 pounds of salt into water, I'm going to try and identify how much of that salt will dissolve and how much will remain at the bottom as a solid white powder. And the salts are going to change throughout this entire chapter. So sometimes we might focus on something like sodium chloride, a salt that you guys ingest all the time. Other times we might look at lead chromate, something that you don't ingest. Okay? We're just saying it's going to break into its respective ions. So we can determine the solubility product as follows. So here would be our salt. The M would be the metal in our salt, or our cation, and its respective subscript. And the X would be the anion and its respective subscript. It's a solid, and it's going to break into its 2 aqueous components. The metal, or the cation, and we're going to put its respective subscript in front as its coefficient. And then we're going to have the anion with its respective subscript as its coefficient, just like we've seen in the previous problem. So let's look at our first problem. Fluorite, calcium fluoride, is a slightly soluble solid that dissolves according to the equation. CaF2 solid breaks into the calcium ion plus 2 fluoride ions. Both are aqueous, since we have a 1-to-2 charge balance. So I have 1 calcium for every 2 fluorides. The concentration of calcium 2+ in a saturated solution of calcium fluoride is 2.15 times 10 to the negative 4 molar. Therefore, that of fluoride is 4.3 times 10 to the negative 4 molar. That is twice the concentration of the calcium. What is the solubility product of fluoride? So let's see how we would solve a problem like this. Like I said, there's always going to be a set way to solve these problems. The first thing is you want to write your ionic equation. In this case, it's been provided for us. Our reactant is the solid calcium fluoride, and our product are its respective ions. Then we want to write the solubility product expression. So here I've written it. My KSP is equal to the calcium ion concentration times the fluoride ion concentration, and we're going to square that fluoride ion concentration simply because it has a coefficient of 2 in front of it. Now, it's just plug and chug at this point. We've been provided the concentration of the calcium ion, 2.15 times 10 to the negative 4. And we've also been provided the concentration of the fluoride ion, 4.3 times 10 to the negative 4. So we can take that 4.3 times 10 to the negative 4, square it, and then multiply it by my 2.15 times 10 to the negative 4. And it tells me the KSP for calcium fluoride is 4 times 10 to the negative 11. That value is just telling me what is my ratio of products to reactants in terms of how well does this salt dissolve. So from this value, if we found a KSP of a secondary salt, we could compare whether or not it would dissolve more or dissolve less in solution. And you can also check your Appendix J and see that this KSP actually matches what's been provided in our table. So let's look at another one. Determination of molar solubility from KSP. So the KSP of copper 1 bromide is 6.3 times 10 to the negative 9. And I want to calculate the molar solubility of copper bromide. The molar solubility just basically tells me how many moles of copper bromide is going to dissolve in 1 liter of solution. Okay? So as we do in all problems, the very first thing I want to do is I want to write the ionic equation, and then I want to write the equilibrium expression. So here we've solved it. So I wrote my ionic equation. My CuBr solid breaks down into its respective ions of copper plus and bromide minus in a 1-to-1 fashion. Then I write my KSP expression. My KSP is equal to my copper concentration times my bromide concentration, each one raised to the power of 1 because of their respective coefficients. And we're not going to divide it by anything because our reactants are always solid. So that's going to be my expression. When you're not told the concentration of any of your ions, you need to put together an ice table. So we're revisiting ice tables back from chapter 13. So here I have my ice table. And I have my I for initial concentration, C for change, E for equilibrium. And on the top, I have my 3 components in my reaction. So the first one I have is my copper bromide. It's a solid, so it's not going to play a role in my equilibrium expression. So I can really just cancel out that first column completely. The next column, I have my copper plus ion, and in my last column, I have my bromide minus ion. The initial concentration of these ions is 0 because initially I haven't thrown my salt into solution yet, so I just have water as a solvent. So my initial concentrations are going to be 0 and 0. My change is going to be a plus X, right? So it's got to be a plus because they are my products, so they are being formed. And the coefficient in front is 1, simply because the coefficient in front of my copper is 1 and my bromide is 1. If there was a different number, that would be what I would place in front of my X value. So 0 plus X gets me X, 0 plus X gets me X. So I can plug that back into my initial equilibrium expression, and I get that KSP is equal to X times X, or X squared. So from there I can say that my KSP is equal to X squared. If I want to solve for my X value, X is equal to the square root of my KSP, and I've been provided the KSP in the problem itself. So my X is equal to the square root of 6.3 times 10 to the negative 9. Therefore, that X value is 7.9 times 10 to the negative 5 molar. When I'm trying to find the molar solubility of copper bromide, since my copper and my copper bromide are in a 1-to-1 ratio, I have 1 copper bromide and it forms 1 copper, whatever my X value is for copper, it's going to be the same exact value for the molar solubility of my copper bromide, because every time 1 copper bromide dissolves, it forms 1 copper plus ion. So if I can solve for my X to be 7.9 times 10 to the negative 5 molar, I then know my molar solubility is also 7.9 times 10 to the negative 5 molar. So I've solved for the molar solubility of copper 1 bromide. So let's take a look at a similar problem. So the KSP of silver iodide is 1.5 times 10 to the negative 16. Calculate the molar solubility of silver iodide. If I were you, I would pause this right now and solve it on your own, and then replay the video from this point on as I solve it myself. It's very, very similar to our previous problem. So the first thing we want to do is we want to put together an ionic equation. So my silver iodide, solid, is in equilibrium and breaks down into its respective ions of silver plus and iodide minus. My KSP is then equal to the concentration of the silver ion times the concentration of the iodide ion. That's my solubility product expression. I always want to write that out next. Since I don't know the concentration of either ion, I need to put together an ice table. So here I have an ice table. On the top I have my silver iodide reactant, and then I also have my silver ion and my iodide ion. The initial concentration of the ions is 0 and 0 because I've yet to throw my salt into solution. My change in concentration is a plus X, so a plus 1X since the coefficient in front is 1. So at equilibrium, I find that the concentration of my silver plus is X and my iodide minus is X. So I can plug those back into my KSP expression. So my KSP is X times X, which is really X squared. So once I know my KSP is equal to X squared, I can take the square root of my KSP to solve for X. So X equals the square root of 1.5 times 10 to the negative 16. Tells me that value is 1.2 times 10 to the negative 8 molar. Since that X value is in a 1-to-1 ratio with my silver iodide, the molar solubility of my silver iodide must also be 1.2 times 10 to the negative 8 molar.